Okay, so we're going to be looking into the length of a curve. And now we have for the length of a curve. And we have going from the endpoint AC to BD. And you can determine the length in either of two ways. Okay, and if we look at it from the perspective of integrating with respect to x, so here the length will go from x is equal to a to x is equal to b, taking the square root of 1 plus the square of dy over dx. And integrating with respect to y, we have integrating from c to d, and we have of the square root of 1 plus the square of dx over dy. And just to start us out, and let's say that if we determine the length of y is equal to 4x plus 1, from 0, 1 to 417. First of all, okay, we can integrate with respect to x. Okay, but for what we have right now, okay, we have y is equal to 4x plus 1 arriving at dy over dx. So taking the derivative in x of both sides, so you have dy over dx is equal to 4, and in the case of the square of the derivative, we have it 16. Now, for the length of this particular curve, so integrating with respect to x, again, I am going from x is equal to 0 to x is equal to 4. And I have the square root of 1 plus the square of dx over, make that dy over dx, which I have to be at 16. One plus 16 is 17. So I have the square root of 17 dx to integrate over. And we have for the antiderivative, okay, so we have the square root of 17 times x, or x times the square root of 17, as x goes from 0 to 4. And in exact terms, the length, which actually turns out to be of a straight line, so from 0, 1 to 417, we have the length is going to end up at 4 times the square root of 17. So, and this is just a calculus version of what we have for the distance formula between points. Now, where we have official curves to come in, and let's say that if I determine the length And we'll say that we have y is equal to 2 times x to the 3 halves. From x is equal to 0 to x is equal to 2. So we have, in this particular setup, so I have that y is equal to 2x, 2 times x to the 3 halves. And we have for dy over dx, so taking the derivative of both sides. So I have 3 times x to the 1 half. So you have 3 halves times 2 is 3. X to the 3 halves goes to x to the 1 half. And upon taking the square of the derivative, three squared is going to be at 9. X to the 1 half squared is just going to be at x. Now, for what we have in the case of the general setup, now we're going to apply numerical integration. But for what we have in the meantime, now we have the integral of the square root of 1 plus 9x dx. And for what we have in this particular integral, we will be looking at u substitution. So I can set u equal to not just 9x, but 1 plus 9x. Taking the differential of both sides, so I have du is equal to 9 dx. And so I have 1/9 of du is equal to dx. And upon following through, so I have the integral of the square root of u, and dx I have 1/9 of du. So I have 1/9 of the integral, and I can just put the square root of u as u to the 1 half du. So I have 1/9 for the antiderivative of u to the 1 half. I have 2/3 of u to the 3 halves, followed by the constant. So I have 2/27 of u to the 3 halves, and we have, with back substitution, I have the quantity of 1 plus 9x raised to the 3 halves. Now, in carrying over officially with the length of this particular curve, so I'm going from x is equal to 0 to x is equal to 2. Again, I have the square root of 1 plus 9x dx. We already had the antiderivative stored. So I have 2/27 of the quantity of 1 plus 9x raised to the 3 halves. Once again, as x goes from 0 to 2. And we have, in the case of the upper limit, okay, we have it 2. 1 plus 9 times 2 is going to be 19. So we have 2/27 of 19 to the 3 halves. And we have minus. Okay, now the lower limit is 0, but this time around the expression is not negligible. We have 1 to the 3 halves is 1. We have times 2/27. So in exact answer terms, okay, we have 2/27 of 19 to the 3 halves minus 2/27. And for the approximate